Here we will try to simulate the Faraday's experiment with permanent magnet moving in the coil. The coil is motionless, the permanent magnet is moving inside the coil, so following the Faraday's law, the electric current is induced in the coil. Our task is to simulate this. I create a new problem. The problem type is magnetics. The model class is axisymmetric. All bodies are cylindrical, have cylindrical form. The length units are millimeters. For the transient problem, you should provide the time stepping. I will skip this step for now and return to this later. Now, again, this is the geometry model editor window. Here you should draw the geometry model. First I will draw the coil. It is 10 by 15. This would be the axis of the rotational. In the axisymmetric problem, the axis of the rotation is a horizontal one, and you should draw only the upper half of the geometry model. Now the coil consists of 200 turns. So I select and the left edge and apply the duplicate operation. And the same for the bottom edge. I select the edge and apply the duplicate operation. Now here I got the multi-turn coil. Now QuickField cannot specify the motion speed in QuickField. You cannot simulate the motion directly. Instead of moving the magnet, I will move the coercive force of the magnet. This is tricky, so I will explain in more detail. Initially, the magnet is placed somewhere here. The magnet is characterized by the coercive force. Next moment, the magnet has moved a little. We cannot modify the model, but we can change the magnet properties. For the magnet, well, I assign the label magnet. For the magnet, we can specify the coercive force as a function of coordinates and time. Let me show you our free utility called the QuickField formula plotter. Please consider the following equation. This is the dependency of the coercive force, and x is the coordinate. Now this dependency also includes the time. At initial moment of time, the coercive force is here. Now as the time changes, the function change to store, and this way we can simulate the motion. So to simulate the motion of the coercive force, I should draw not the actual permanent magnet but some large extended permanent magnet, extended block. Initially the coercive force will occupy only small element, then it will move along this magnet, and this way will simulate the motion. Let me show you already prepared problem. You see, this is the coil with many turns, and this block is labeled as magnet. But for this block, the coercive force is specified as the function of coordinates. And if we take a look at the result, at initial moment, we will see that our magnet is located here. Well, some next moment of time the magnet is located here, then here, here, and this way we simulate the motion of the permanent magnet. Now let's take a look how this motion affects the current induced in the coil. You see, indeed, there is the electric current induced in the coil, and if we take a look at the circuit coupled with this coil, we can see that in this coil the electric current is induced. Initially it was a very small current, but then as the magnet approaches the coil, the current rises rapidly. Then after the magnet enters the coil and passes inside the coil, the current drops to zero. And then we can see the reverse process. You see there are several time layers, and for each layer, each time corresponds to the specific position of the magnet. Now that is possible with QuickField 6.3 Series Part 2. In previous version it was not possible to simulate this at all.